Imagine a pair of stars so strange that every heartbeat they make bends time itself, so heavy that a mountain could fit beneath a millimeter of their surface, so relentless that they are erasing their own orbit day by day, not in an explosion, but in silence. This is not just another story of dying suns. It is the chronicle of the most destructive system ever discovered. Two neutron stars locked in a dance that steals time from clocks, energy from light, and distance from space itself, until nothing remains but a black hole and the echoes it leaves behind. Stay with this story, because every clue, every detail, will lead you closer to understanding how destruction can be both patient and absolute, and why it all began with two ordinary stars that simply ran out of ways not to fall. But to understand why this system is so destructive, we have to rewind time, back to the moment when two ordinary suns began their long journey toward collapse. In the wide black between the lights, a place holds two objects so small they would vanish against a fingertip held to the sky, yet so heavy they convince space to bend around them. They rotate with a precision that feels ceremonial, and they circle one another in a pattern that looks simple until time near them starts to misbehave. Their presence persuades even light to hesitate, to yield a sliver of its path. Their gravity does not announce itself with flame or color. It works by taking what seems untakeable: seconds from a clock, straightness from a ray, calm from a crust that wants to be still. The setting is deep within Puppis, far beyond the local dust and the familiar lanes of nearby stars. Here, noise is a field of soft, ancient photons and the scattered grains of old explosions. Into this field, the pair writes a record in pulses, a dotted line that only instruments can read, a language of arrival times and tiny delays. The message is steady, yet nothing around them is truly still. Not the beams that rake outward like thin searchlights, not the space that carries them, not the relentless trade the system makes. Motion for heat, order for wave, distance for certainty. They are called by a string that sounds like a cipher, PSR J0737.
Close. Closer than seems polite for stars. And at every nearest point, the rhythm inside each object slackens by the width of a breath that no lungs could draw. The effect is not a mood, but a law. Time itself dilates, as if taking a slow step to avoid being torn. The pulses lag by an amount so slight it hides between heartbeats, and then the rhythm returns, as if nothing had happened, though something always has. Their environment is a foundry with no flame. Wind exists as particles offered up by fields, as thin rain that never wets, as a drift of charges guided by magnetism so strong it gives shape to emptiness. Where their beams sweep, they etch arcs into darkness. Where their magnetospheres touch, they comb each other's weather. The eclipses are events without shadow, not the occlusion of light, but the bruising of a signal. A red stretch when gravity reaches out to the passing pulse and pockets a little of its energy. Even the path they follow refuses to stay put. A mark that should be fixed, the place of closest approach, slides forward each year by a bold fraction of a circle, as if the orbit were a ring turning inside its own plane. Long ago, a small planet closer to a local star showed a milder version of the same trick, and its shift taught a new theory to speak. Here, the lesson writes itself with heavier ink. From a distance, the pair could be mistaken for stability, periodic signals, repeating geometry, a system that keeps its appointments. But every repetition is purchased. Each circuit leaks a sliver of energy into ripples that race outward at light's limit. Waves not of water or air, but of the shape of space itself. The waves are faint and wide, attacks paid in silence. Yet the balance sheet is inexorable. separation shrinks by measures that would look petty on a ruler and look fatal on a timescale. A daily loss measured in fractions of a finger's width becomes, across patience, the guarantee of a future collision. The destructive power here is not only in endings, but in the way endings begin. Slow, precise, almost gentle. Around them, emptiness keeps its counsel. If any worlds once circled here, their history Earth, steady and ordinary. And yet it listens across thousands of light years to seconds that strain and relax like a chest underwater. The mystery is not whether destruction will arrive, but how destruction can be so patient, so measured, and so complete. The dance we see today is only the aftermath. To know how it began, we must look at the final seasons of the giants that came before. In the quiet arm of Puppis, long before the pulses began ticking, 2 elder suns moved through their final weather. Their light had softened, their outer layers had swollen and cooled, and deep inside, the last reservoirs of fuel were being coaxed into one more round of fusion by pressure alone. For ages, gravity and fire had held a fragile truce. Now that balance thinned, then faltered, as if a bridge sagging plank by plank under its own weight. The stars did not announce the change with spectacle. They simply allowed their cores to grow heavier and more reluctant to support the shells above. The ending began as endings often do in astronomy, slowly, imperceptibly, and then all at once. The first collapse was a precision event disguised as chaos. With fusion no longer able to prop up the interior, the core surrendered to gravity, dropping inward in a rush that heated matter beyond endurance and ignited a last, runaway burn in the surrounding layers. A shockwave unspooled, threaded with neutrinos escaping as if through every door at once, carrying energy outward faster than light could carve a path through the choking interior. The star's elaborate architecture, onion skin shells of elements arranged by the temperatures that birthed them, unraveled in a handful of heartbeats measured on the clock of stellar physics. The outer skin tore away and ran, a storm of incandescent gas blooming into a newborn remnant nebula, while the core rebounded as something smaller, darker, and inconceivably denser. In the debris, grains and filaments curled back on themselves like smoke in slow motion. The shock front, still muscled by momentum, slammed into the companion red giant. The second star, already near its own threshold, found that nudge enough to cross the line. Its interior buckled, space left between. A crust only meters thick learned to carry stresses that would pulp mountains elsewhere. Beneath that layer, an ocean of neutrons pressed outward while gravity pressed inward, and the compromise they struck produced an object small enough to be crossed in minutes at terrestrial speeds, yet heavy enough to tug on light. The new stars did not shine in the old way. They spoke in pulses and in winds, in fields and in the tiniest changes of timing. Such remnants are not the default outcome of starlight. Most stars coast toward gentler retirements, shedding mass over long spans and ending as white dwarfs that cool into hypothetical black dwarfs over distances of time too large to stage in a single telling. Only when a star begins life with heft, more than about 8 times the sun, does it spend its last seasons building an iron heart and staging the prelude to collapse. If the final core is too heavy, the fall continues past any resistance and a black hole is born. If the core lands in a narrower band, between roughly the heft of 1.5 suns and a little over 2, the matter holds as neutrons, and a neutron star takes the role. The path is set not by preference, but by mass, that first decision made in the cradle of the nebula with a star condensed. Rarity follows from these gates. In a galaxy that counts stars the way a shore counts grains, neutron stars are the exceptions. By the best census, only one out of many hundreds stands in that category, and fewer still reveal themselves as pulsars with beams aligned just so. They are difficult to see with human eyes because they do not spend their days in the visible, but X-rays, radio waves, and the exquisite patience of timing pull their presence from the noise. The pair in Puppis would, in time, be known as PSR J0737-3039. But in these first moments after the double blast, they were unnamed, simply two fresh neutron stars, gravitationally bound by proximity and heritage, spiraling toward a common center, because there was no longer enough energy left in their system to keep them far apart. Even as they cooled from furnace to embers, the newborn objects worked on their surfaces with invisible hands. Gravity, magnetism, electrostatic repulsion, fog, etching the memory of the catastrophe into the local medium. Any ancient worlds that might have circled the giants were either erased or exiled. Any new worlds would, at best, have to assemble in a storm of high-energy particles and shifting fields. The newborn neutron stars offered little hospitality. Their magnetospheres yawned wide. Their particle winds made weather of a kind that had no seasons, only flux. In that environment, survivals and accretions were not impossible, simply inhospitable. From the vantage of deep time, the decisive fact was not the light, but the loss. The double supernova had robbed the system of mass and order. The binding that remained tied the remnants together in an orbit already compact compared with ordinary stellar couples. With every circuit, energy would bleed away as gravitational waves, and the distance between the two would shrink by measures too small to impress a ruler, but all too persuasive to the arithmetic of millions of years. The scene looked calm because most violence had already happened, yet it contained a promise that could not be revoked. The system was set. 2 clocks in one cage, 2 lighthouses sharing a horizon, 2 survivors that had traded the abundance of their former lives for density, precision, and a future sealed by the very laws that allowed them to exist. And so, the last seasons of the red giants ended not with fading, but with conversion. Heat became motion. Motion became waves. Shells became nebulae. Cores became neutron stars. In Puppis, the ledger closed on one chapter and opened another, in which time would stretch and orbits would precess. Signals would redden, and pulses would be delayed. All effects waiting, like tools on a bench, ready to shape the story still to come. The catastrophe had passed. The consequences had only begun. The explosions left behind more than wreckage. They created 2 rare survivors, neutron stars. And rarity is the key to their story. In the great population of stars scattered through the Milky Way, variety hides behind repetition. Instead, their outer layers drift away as planetary nebulae, leaving behind a core no larger than Earth itself. This white dwarf, though dense by human standards, is tame compared with the compact monsters produced by larger stars. Slowly, over trillions of years, it will cool into darkness, a black dwarf that the universe is still too young to have made. But mass beyond that threshold transforms endings into catastrophes. A star more than 8 times as heavy as the Sun cannot escape the fate of collapse. For those with cores settling between roughly 1.5 and 2.5 solar masses, gravity forces protons and electrons to combine, squeezing matter into neutrons. Atoms, as we know them, no longer exist. What remains is a neutron star, small enough to cross in minutes, dense enough to drag even light into hesitation. Push the mass still further, above the limit where even neutrons can withstand the pressure, and the collapse refuses to stop. The result is a black hole, a prison from which no information escapes, a final silence. These dividing lines are not flexible. They define the stellar census as clearly as borders on a map. White dwarfs are the common citizens of stellar afterlife, numbering in the hundreds of millions across the galaxy. Black holes, though dramatic, are less numerous but still far more frequent than their middle sibling. Neutron stars sit in between, born from a narrow corridor of initial conditions and reduced further by the violence of their creation. For every few hundred stars that end their lives, only one may compress into such an object. Rarer still are the ones we can find. Not every neutron star announces itself. Many rotate without the proper alignment to sweep their beams toward Earth. The discovery of pulsars, neutron stars whose magnetic poles and beams are tilted relative to their spin, gave astronomers their first reliable sightings. Like lighthouses on a dark coast, their radio pulses struck with metronomic regularity, ticking through the static as if the universe itself had wound a clock. These signals, arriving with a precision better than most human machines, became a map, proof of invisible corpses left behind by vanished giants scattered across the galaxy. Yet pulsars are not only rare, they are selective. The beams are narrow, the existence allows astronomers to weigh physics itself. They are accidents of timing and alignment, born of precise mass, violent death, and improbable survival. This census tells a story not of abundance, but of exception. The cosmos prefers moderation, stars that live long and die quietly. Only occasionally does it deliver the narrow conditions that forge neutron stars, and more rarely still does it orient them to sweep their signals across our instruments. What is scarce becomes precious. In the scattered pulses from these remnants, humanity has glimpsed the structure of space-time itself, and in the double pulsar, it has found a system so rare that it became both laboratory and omen. From the outside, the galaxy glitters with countless lights, each a candidate for life, for story, for collapse. But only a fraction hide the dense, spinning hearts of neutron stars. To trace them is to count the survivors of extraordinary violence, each one a statistic against the overwhelming tide of ordinary endings. A census of rarity drawn from the universe's own reluctance to repeat its extremes. Among these rare objects, PSR J0737-3039 is rarer still. To see why, we must place the pair under a closer lens. In the constellation of Puppis lies a system unlike any other we have measured. Catalogued as PSR J0737-3039, it carries the dry precision of coordinates, yet behind that label is something extraordinary. Two neutron stars locked together, both active pulsars, both flashing their signals with mechanical persistence. They circle each other inside an orbit so compact that it belongs less to the scale of stars and more to the habits of machines. Here, the cosmic and the ordinary overlap in unsettling ways. The orbital period is barely over 2 hours. In the time it takes for a human commute from one city to the next, these collapsed remnants complete a full revolution around each other. Where ordinary binary stars take days or months to swing through a cycle, these do so while a clock still measures minutes. Every orbit is a breathless race, the two corpses tracing tight ellipses through warped spacetime, their timing so strict that it rivals the very atomic clock
than a billion tons. Their crusts are lattices that crack in millimeter ridges heavier than mountains. Their cores, seas of neutrons bound in densities untested anywhere else in nature. And both rotate in pulses, sending beams into space
that sweep like the second hands of cosmic watches. What makes this system unique is that both lighthouses can be seen. Their beams are angled just right to sweep across Earth, allowing astronomers to record two separate sets of pulses, two clocks ticking inside the same gravitational cage. This double signal is a laboratory without rival. Every orbit and every pulse becomes a data point, every variation a chance to weigh the forces predicted by Einstein and to watch gravity shave time itself. Already, patterns reveal themselves. At their closest approach, the pulses arrive just slightly delayed, stretched by the gravity of their companion. The point of nearest distance, the periastron, shifts each year by a measurable fraction, echoing the famous precession of Mercury's orbit, but amplified to a degree that can be seen without waiting centuries. Where our planetary neighbor hinted at relativity, this system declares it openly, orbit by orbit. The scale of this dance is deceptive. To imagine it is to picture two objects no larger than cities circling each other inside a distance the size of the sun, repeating the act every 2 hours, each revolution sending ripples across the universe. The numbers appear small, but the consequences are vast. Every pulse we record is a signature of stress, of loss, of inevitability. For now, the system appears balanced. Two clocks keeping their beat, two corpses circling in a rhythm steady enough to plan around. Yet the stability is an illusion. Each cycle shaves a fraction of energy from the orbit. Each wave that departs carries away a sliver of motion. Each year brings the pair closer by a distance almost invisible to the human eye. The cage is closing. Put a pin in these scales. A 2-hour orbit, a sun-sized separation. A pair of stars the size of cities. They may read like curiosities, like extremes noted in the margins of a catalog. But the earthly sense. A thin sheath of plasma clings to the surface, no thicker than a whisper, charged and restless under the star's magnetic fields. This veneer radiates in X-rays and radio bursts, the residue of a star that once blazed with fusion, but now shines only through its own instability. Beneath that layer lies a crust like no stone on Earth. Atomic nuclei, packed so tightly they resemble a crystalline lattice, form an unyielding surface that resists the crushing pull of gravity. But only just. Stress builds invisibly in this crust. As the star spins, as it interacts with its magnetic field, as its orbit with a companion tugs rhythmically at its skin, the lattice cannot remain perfectly stable. It cracks. It shifts. It shudders in what astronomers call a starquake. On Earth, a fault line slipping by a meter can level cities. On a neutron star, the crust moves by the height of a fingernail, a ridge only a millimetre high. Yet that millimetre, under the burden of gravity 10 trillion times stronger than our planet's, carries the weight of mountains. When such a fracture occurs, energy floods outward in sudden releases. The neutron star's rotation may jolt, its timing stuttering for a fraction of a second, a glitch recorded by astronomers as though the universe's clock had skipped a beat. What appears to us as a tiny irregularity in pulses is, in reality, the crust of a collapsed sun, tearing under forces no solid surface can truly withstand. Each starquake is a reminder that even the hardened shell of a neutron star is fragile compared with the pressures locked beneath. Deeper still lies the inner crust, a realm where the rules of ordinary matter begin to fray. Here, neutrons begin to drip from nuclei, creating a superfluid ocean beneath the rigid shell. It is this uneasy boundary, the solid lattice above and the fluid depths below, that feeds the quakes. The crust anchors itself against unimaginable pressure, but the sea beneath shifts and flows, straining the outer layer until it yields. The result is a cycle of glitches in pulses, changes in spin, irregularities that tell us the surface is never truly still. From the outside, these quakes are mere anomalies, tiny bumps in an otherwise regular pattern. But within, they are tectonic upheavals. The crust shifts by millimeters, the magnetic fields flicker, radiation bursts outward, and energy flows into space. What we record as a skipped heartbeat in the star's rotation is, in truth, a reminder that the surface of a neutron star is alive with strain. These millimeter landscapes are not permanent. Gravity smooths them quickly, forcing the crust back into balance, but scars remain in the signals. To study them is to glimpse the hidden violence beneath the surface, to hear the groan of matter packed past its limit. And as small as they are preludes to greater losses. The quakes reveal what happens when stress accumulates and when closeness, whether of crust and core or of star and star, forces inevitable release. On Earth, landscapes are mountains, valleys, plains. On a neutron star, landscapes are measured in millimeters, each one heavier than worlds. It is a reminder that in a place where gravity is cruel, scale is deceptive. Tiny becomes catastrophic, and catastrophe becomes routine. These ridges and cracks are the handwriting of forces that do not forgive movement, a script that will continue to write itself until the system itself collapses. If millimeters weigh like mountains, what then lies deeper inside? The answer pulls us into the cores themselves. Beneath the trembling crust of a neutron star lies a world stranger still, a realm where matter abandons the familiar rules of chemistry, and even the language of ordinary physics begins to fracture. The deeper one descends, the more impossible the conditions become. Pressure rises until atomic nuclei, once stable, can no longer maintain their form. Electrons are driven into protons, merging to create neutrons, while neutrinos, those almost massless phantoms, slip free, carrying with them the excess energy like silent thieves of heat. What remains is a substance so dense that it resists imagination, an ocean of neutrons pressed together until they behave less like particles and more like a single collective state of matter. Here, the laboratories may hide states of matter that remain speculative. One hypothesis proposes quark matter, neutrons broken down into their fundamental constituents, quarks, freed from confinement to form a dense, exotic soup. In this vision, the innermost heart of the neutron star is not neutrons at all, but a quark sea, swirling at densities where ordinary physics falters. Other models point toward hyperons, particles heavier than neutrons, born when strange quarks emerge under extreme compression. These hyperons could pack together in the core, altering the star's structure and changing the maximum mass it can sustain before collapsing into a black hole. Still other theories suggest more intricate pasta phases, structures where nucleons arrange themselves into shapes reminiscent of sheets, rods, or bubbles. Strange architectures formed not by chemistry, but by sheer nuclear pressure. The difficulty lies in proof. The distances are immense, and the conditions cannot be recreated on Earth. Particle accelerators push matter close to these extremes, but only for fleeting instants and in far smaller volumes. What happens inside a neutron star unfolds over kilometers and persists for millions of years. Our instruments can only infer, drawing clues from timing irregularities, from gravitational wave signals, from the maximum masses of known neutron stars. Each hypothesis, quark seas, hyperon cores, nuclear pasta, remains just beyond reach, tantalizing, unconfirmed. What is certain is that the cores are not static. They rotate, they exchange energy with the crust,
and they bleed away heat through neutrinos for thousands of years. Slowly, they cool, but never enough to lose their exotic state. Within them, quantum effects dominate the behavior of bulk matter, turning the core into the largest known quantum object in the universe. Every neutron star, then, is both a grave of a collapsed sun and a living laboratory of extremes, holding answers that may only be unlocked by the violence of collisions or the precision of future observatories. The double pulsar in Puppis is not just a pair of clocks circling each other. It is a pair of riddles, each core holding the possibility of phases of matter that humanity has never observed directly. When they finally meet, the merger may reveal in gravitational waves circle each other, trading motion for something invisible, paying a toll in energy that slips away into the fabric of the cosmos. From a distance, their dance seems perfect, precise, endlessly repeating. But hidden within that precision is a constant drain. With every revolution, the system loses just a fraction of its strength. The price is not sound or light, but something subtler, a ripple in space-time itself. These ripples are called gravitational waves. They are not waves in air or water, but waves in the very shape of space and time. Imagine stretching a fabric so taut that even the faintest touch sends vibrations racing across it. The double pulsar touches space-time with every orbit, creating undulations that travel outward at the speed of light. They are faint, impossibly faint, so much so that by the time they reach Earth, they shift distances smaller than the width of an atomic nucleus. Yet their existence means that energy is leaving the stars, carried away in silence. The result of this loss is inevitable. The orbit shrinks. Each day, the two stars draw imperceptibly closer together. The amount seems trivial, only a few millimeters, perhaps a fraction of the width of a human hair, but the arithmetic of time transforms trivial into profound. Day after day, orbit after orbit, those millimeters accumulate into kilometers, and over millions of years, into catastrophe. The cage that holds the two clocks is closing, not by sudden violence, but by patient erosion. To picture it is to imagine a couple dancing on a floor that slowly contracts beneath them. They do not stumble, for the shrinking is too gradual to notice in the moment, but every step brings them closer to the center. Their dance is perfect, and yet it contains their undoing. The waves carry away not only energy, but also information, broadcasting the rhythm of the orbit to the universe. The system is whispering its fate into space-time itself, a message that will be heard by detectors across the galaxy when the finale comes. The concept is simple, though the consequences are immense. Gravitational waves are the only known way to bleed energy from such a closed system. Without them, the double pulsar might circle forever. With them, a future where closeness becomes collision. The daily loss is a ticking metronome, patient, unrelenting. This is the art of losing energy, quiet, elegant, invisible. The system does not flare or roar as it decays. Instead, it leaks momentum into space-time, writing its demise into the geometry of the universe. To human senses, the loss is imperceptible. To physics, it is undeniable. And though the collapse will not happen for 100 million years or more, the ending is already underway. Every orbit is a farewell, every wave a small departure, every millimeter a reminder that even the most precise clocks cannot resist the art of loss forever. ECC liberty shrinks, but relativity adds more distortions still, bending time, stretching light, and shifting landmarks. In the double pulsar, time itself refuses to behave. Every orbit is a stage where relativity makes its presence known, bending rhythms and stretching signals, in ways that would be imperceptible anywhere else, but here become undeniable. The closer the stars draw to each other, the more gravity seizes control of the clocks that beat inside them. Their pulses, usually so exact, slow, as if held by an unseen hand. Then, once the orbit carries them apart again, the rhythm quickens, returning to normal, only to repeat the cycle on the next approach. This effect is called time dilation. Gravity does not simply pull on matter, it pulls on time as well. In the grip of such extreme mass, seconds lengthen, and every clock, whether mechanical, digital, or the spinning beam of a pulsar, must obey. The pulses we detect from Earth stretch slightly at each close pass, their intervals lagging by microseconds. Delays so small that only precise instruments can record them, yet so significant that they reveal the strength of relativity at work. Time itself flows unevenly in the binary, breathing in and out with the orbit. Alongside time's distortion comes another trick: gravitational redshift. As the pulses climb out of the neutron star's deep gravitational well, they lose energy. Their wavelength stretches, occurring far more rapidly than in any planetary system. For comparison, consider Mercury. The innermost planet of our solar system also experiences a shift in its orbit, its periastron advancing by a tiny amount each century. It was this anomaly that first forced astronomers to accept Einstein's explanation that gravity is not a force pulling across space, but the warping of space and time themselves. In Mercury, the shift is subtle, accumulating over decades of careful observation. In the double pulsar, the effect is magnified by hundreds, occurring within years, a living demonstration of relativity written in pulses instead of planetary motion. What Mercury whispered, the pulsars shout. The shy precession of a planet around the Sun is a faint echo of the bold migration in Puppis, where every orbit redraws its own geometry. The same principles apply, but here the scales are sharper, the signals louder. What could take a century to prove in our solar system is confirmed in days or weeks among the double pulsars. Together, these effects, time dilation, gravitational redshift, and orbital precession, transform PSR J0737-3039 into a natural laboratory. It is not only two stars in orbit, but two clocks in conflict with gravity, two beams stretched and delayed by spacetime, two objects tracing ellipses that refuse to remain still. Time lengthens, signals redden, landmarks migrate. To observe them is to watch relativity in action, not in abstract equations, but in the beating heart of the universe itself. And as the system continues its dance, these relativistic beats will grow only stronger, the distortions more pronounced, until the orbit collapses into merger. The illusion of stability hides the truth. Gravity is already rewriting time, color, and motion with every revolution, as if reminding us that even the most precise systems are subject to the bending of the cosmic stage beneath them. Heeding that is not the full story. Beyond gravity's grip, the system storms with magnetic weather unlike anything else in the sky. Beyond the crushing gravity and distorted time, the double pulsar reveals another layer of strangeness. Weather. Not weather of air and cloud, contest of strength. A cosmic weather front where invisible storms crash together. Boundaries bend, reconnect, and snap, releasing bursts of energy into the void. For us, the proof comes in the pulses. Normally, a pulsar's beam arrives with the regularity of a metronome. But in this binary, those beams do not always shine cleanly. One star's magnetosphere sometimes eclipses the other's signal, scattering or distorting the pulses before they reach Earth. What was steady
becomes stuttered. What was precise becomes broken by interference. The beams blink, fade, and flare again, their rhythm altered, not by the star's own rotation, but by the weather of its companion. It is as though two lighthouses stood on the same headland, their beams sweeping the sea, but each foghorn interfering with the other, each gust bending the path of light. To the instruments that listen from Earth, these interruptions become audible in their own way, gaps in the ticking, distortions in the signal, bursts of static where silence was expected. By translating the invisible dance of magnetic fields into data, astronomers hear the atmosphere of a world without air. The scale of this weather dwarfs any terrestrial comparison. Each magnetosphere can extend tens of thousands of kilometers, far larger than Earth itself, and the currents flowing through them carry energies beyond any human-made accelerator. Where they clash, they carve unseen auroras into emptiness, not of light we can see, but of radio noise and high-energy particles scattering outward. This environment is not static. With every orbit, the geometry changes. The stars eclipse one another's winds, altering the flow of particles and the brightness of beams. Some pulses arrive weaker, some stronger, some shifted in phase. The timing irregularities are not flaws in the stars, but signatures of their weather. An atmosphere not of molecules, but of fields, tides, and storms. For those who study them, the pulsar's magnetospheres are both an obstacle and a gift. They complicate the clean signals needed to test relativity, yet they also reveal layers of physics otherwise unreachable. In the interruptions and distortions, one can glimpse how plasma moves under unimaginable fields, how particles behave when forced to obey not just gravity of storms. But could any world endure such storms? The search for planets reveals just how hostile this system has become. If here were ever planets circling the two giants that once blazed in Puppis, their fates ended in violence. The double supernovae did not simply strip away atmospheres or shift orbits. They erased stability itself. Shockwaves tore through any companions, radiation sterilized anything that remained, and the loss of stellar mass flung gravitational balances into chaos. Worlds that once may have circled calmly were either ejected into the cold dark or shredded into debris. Could planets have formed again afterward, from the ashes of those explosions? In principle, yes. Supernova debris often seeds new beginnings, creating disks of material that can, in time, gather into planets. But in PSR J0737 339, the environment resists such hopes. The neutron stars spin with ferocity, their magnetic fields lashing out, their particle winds scouring nearby space. Any disk that tried to coalesce would be torn apart before it could grow. Instead of calm accretion, there would be turbulence, bombardment, and radiation so intense that matter itself would be stripped of cohesion. Even if a planet somehow managed to survive or assemble, what sort of world would it be? It would not be a place for oceans or skies. It would orbit close to collapsed suns, bathed in X-rays, bombarded by relativistic particles, and tugged by tides strong enough to tear continents apart. The radiation would sterilize every surface, and the gravitational stresses would distort its interior, squeezing and stretching with every orbit. Days and nights would be meaningless, replaced by flashes of pulsar beams sweeping across the planet like relentless searchlights. Some astronomers have speculated about pulsar planets in other systems, rare survivors discovered by timing irregularities in pulsar signals. These worlds, if they exist, are strange and hostile, born either from fallback debris or captured from other stars. But in the case of the double pulsar, even this possibility borders on the impossible. The binary orbit is too tight, the storms too violent,
the gravitational dance too unstable.
They are destructive, relentless, and final. In Puppis, the double pulsar is not a nursery for worlds, but a graveyard for them. A system where matter has been pushed past gentleness into extremes. What remains is only the binary itself, two compact remnants circling each other in tightening orbits, their environment stripped clean. Planets did not survive. New ones could not form. And if any stray body still drifts there, its existence is a nightmare written in radiation and tides, a monument to survival in a place that never wanted survivors. This is not a system of worlds. It is a system of endings, a reminder that not every star's legacy is a solar system of planets, and not every explosion clears the way for new life. Sometimes what follows is not rebirth, but erasure, a stage where only the most compact and unforgiving objects remain, locked in a dance that allows no companions. No planets remain, only the stars themselves. And the closer we look, the more we see how small measures hide immense destruction. The double pulsar is a master of deception. To the distant eye, it is a calm binary, two faint stars circling each other with mechanical precision. Their pulses arrive in steady rhythm, their orbit repeats without interruption, and nothing about the system appears unusual. Yet every measure hides a contradiction of scale. What looks small becomes immense. What seems trivial becomes catastrophic. This is a place where units we dismiss in daily life, millimeters, centimeters, microseconds, are the key to destruction. Consider the cracks in the crust. On Earth, an earthquake might split the ground by meters, reshaping cities and rivers. On a neutron star, the crust yields by mere centimeters. Yet those centimeters release energy equivalent to the detonation of countless nuclear weapons. The lattice of matter, compressed to densities beyond comprehension, does not forgive small shifts. A centimeter is enough to rattle the entire star, to alter its spin, to send a pulse glitching across light years. Or think of the mountains. No higher than a millimeter, these ridges would pass unnoticed beneath a fingertip. But on the neutron star's surface, gravity magnifies their weight to more than Everest, decisive in understanding the system. Each delay reveals time dilation, redshift, precession. The entire structure of relativity writes itself in those fractions, tiny gaps in rhythm that prove gravity bends time and space. What the eye cannot notice, instruments capture, and in those microseconds lies the story of inevitability. The system thrives on these misdirections. It makes the immense appear small, the small appear immense. It persuades us that nothing is happening, when in fact catastrophe is already underway. Each crack, each mountain, each delay is a signature of forces that will in the end collapse the stars themselves. This trickery is not malicious but structural. Gravity at such scales does not allow for moderation. Every unit of distance, time, or weight is magnified until it breaks the link between intuition and truth. The closer one looks, the more destructive the system becomes. What seems a calm binary turns out to be a furnace of strain and loss, writing its story not in spectacular flares, but in tiny increments, each one carrying the weight of worlds. PSR J0737-3039 is, in this sense, a teacher of humility. It reminds us that our eyes are poor judges of scale, that numbers which feel insignificant on Earth can rule entire systems in space. Centimeter cracks, millimeter mountains, hour-scale orbits, microsecond delays. These are the measures of its reality, and in those deceptive measures lies the truth. The system is not stable, not calm, not ordinary. It is a trickster of scale, hiding destruction in the smallest details, patient in its unraveling, relentless in its outcome. Each detail is a clue, each anomaly a sign. Together, they form a record, a book of signals written across space and time. For most of human history, the cosmos was silent. Stars shone as points of light, planets wandered slowly across the sky, and the only messages we could read were in brightness and motion. But the arrival of radio astronomy in the 20th century cracked open that silence. For the first time, the sky was not only something to see, but something to hear. The first hints of neutron stars came through radio waves, faint pulses hidden in static,
of crusts under strain, of magnetic weather, of surfaces cracked by forces no rock could endure. Where radio had traced timing, X-rays traced temperature and violence. Together, they painted a fuller picture. Neutron stars were not just clocks, but furnaces of extremes. The art of timing soon followed. Astronomers realized that every pulse could be marked, measured, and compared. Like strokes of calligraphy, the ticks of pulsars formed intricate scripts across decades of observation. A single deviation in rhythm might point to a starquake, a drifting orbit, or the subtle tug of gravitational waves. Timing became not only a method, but a language. Each pulsar wrote its autobiography in beats, and humanity learned to read those beats as words, written in space-time itself. With time, these signals grew into an atlas. Hundreds of pulsars were catalogued, scattered through the Milky Way like beacons along invisible roads. Some spun every second, others every millisecond, flashing so rapidly they blurred into vibrations. Some sat alone, isolated relics adrift in emptiness. Others orbited companions, white dwarfs, normal stars, or fellow neutron stars. Each one added a new page to the growing book of signals, each page refining our understanding of matter under crushing weight and gravity in its purest form. And within that atlas, PSR J0737 to 3039 occupies a chapter of its own. It is not just another pulsar, but a pair, both beams aligned with Earth, both clocks running in tandem. Their combined signals are a dialogue written across the cosmos, offering double the data, double the confirmation, double the chance to test what no laboratory on Earth can reproduce. Where most pulsars offer one heartbeat, this system offers two, intertwined in a rhythm that maps relativity itself. To study them is to read not just a book, but a manuscript of laws. The delays, distortions, and eclipses become ink strokes in a record written by gravity. Each measurement confirms or challenges theory, each page bringing us closer to truths hidden deep inside matter. The book of signals is not finished. It is ongoing, off invisibly by gravitational waves. The loss is so slight it seems meaningless, only a few millimeters shaved from the orbit every day. Yet astronomy teaches patience. What vanishes today returns multiplied across centuries, millennia, and millions of years. Imagine the orbit as a vast dance floor, just wide enough to hold the two collapsed stars. With every step, the floor tightens. It does not collapse suddenly, but shrinks by imperceptible amounts, closing fraction by fraction, until the dancers can no longer move without colliding. Their graceful revolutions, repeated thousands of times each year, are each marked by a tiny deduction. Each orbit pays a toll, and the toll is written into the future. The numbers tell the story with stark clarity. 7 millimeters a day, a few meters a year. Over the span of a human lifetime, the stars draw closer by the length of a football field. In the span of recorded history, by several kilometers. These distances are still small compared to the sun's size, but they accumulate with relentless certainty. The universe has time enough for patience. Project the losses forward, and the outcome sharpens. In tens of millions of years, the stars will be locked in a tighter embrace,
their orbits accelerated, their gravitational waves stronger. What begins as a whisper will rise to a roar, detectable across the galaxy. The pulses, once steady, will distort and break as the beams are swallowed by magnetic storms and tidal forces. The dance floor will be nearly gone. Even now, instruments on Earth can measure the shrinkage. Each pulse arrives slightly earlier or later than predicted, the subtle timing revealing the orbit's gradual contraction. These are not guesses, but direct observations, a ledger maintained by the stars themselves. Every delay, every glitch, every stutter is an entry in the record of losses. Astronomers do not have to imagine the shrinking. They can watch it happen, year by year, confirmed by data as precise as any clock humanity has built. And so the binary becomes not only a pair of stars, but an accountant of time. Each orbit subtracts from the balance. Each revolution consumes the future. The stars are spending their existence 1 millimeter out, spending its future one orbit at a time, until the balance reaches zero and the dance ends in collision. The floor is closing, the toll is due, and the system continues to pay. And as separation shrinks, thresholds await. Tides grow, pulses distort, and the last calm revolutions approach. The fate of the double pulsar is sealed not in sudden violence, but in thresholds crossed, one by one. As the stars spiral closer, their separation falls beneath the margin where stability can be trusted. What was once a wide and steady orbit shrinks into danger, each revolution bringing the companions nearer to forces neither can withstand. The system still circles with clock-like rhythm, but beneath that order, stress builds. First come the tides. Gravity pulls not just on the stars as wholes, but on their very crusts. The neutron-rich shells, once brittle but resilient, begin to groan under the shifting tug of their companion. With every pass at closest approach, the strain deepens. Starquakes fracture the crust, millimeter ridges rise and collapse, energy bursts outward in invisible storms. The surfaces crackle with stress, preparing for failures more violent than any quake before. Then, the beams begin to distort. The clean pulses that once swept across the galaxy with metronomic precision falter. Magnetic fields buckle under the strain of proximity, bending and twisting the paths of charged particles. The lighthouses flicker, blink, and fade, as though the stars themselves are losing their voices. For observers on Earth, the rhythm that once seemed eternal becomes ragged, a pattern fraying at its edges. The system is no longer the tidy clockwork it once appeared. The orbit tightens further. What once took hours now takes minutes. Acceleration climbs, gravitational waves strengthen, and space-time itself carries away more and more of the star's energy. Each circuit becomes a sprint, each pass more violent, each toll heavier. The stars circle not in balance, but in desperation, held together by gravity, yet torn apart by its extremes. Inside, their cores resist as best they can, but even neutrons are not invulnerable. Tides stretch the stars into ellipses, straining,
Written in fading pulses. Then the distortions will overwhelm the signals, the crusts will fracture beyond repair, and the final plunge will begin. Approaches and thresholds define this stage. Tides too strong, beams too bent, separations too narrow. The binary has no choice but to cross them all. The last clean pulses will mark the end of stability, the final breaths before collapse. What follows is the merger, the moment when every stress and every loss reaches culmination. But for now, in this quiet tightening, the stars still circle, silent, patient, doomed. Proximity, collisions, the inevitable. The stars collide, space-time rings, and a black hole is born.
The end does not arrive as a single strike, but as a culmination, a moment when all the losses, fractures, and distortions converge into collapse. The two neutron stars, after millions of years of circling, reach the point where no orbit can hold them apart. Their separation shrinks to nothing, and gravity claims its final due. Space-time itself writhes under the violence. The orbit, once smooth and predictable, unravels in a final frenzy. Distances collapse, accelerations surge, and the very geometry of the universe twists as though wrung by an unseen hand. Waves of distortion ripple outward, no longer the quiet whispers of gradual loss, but a roar in the fabric of existence. No ear can hear it, but detectors scattered across the galaxy would tremble in unison, registering the thunder of space-time itself. Matter resists, but only for an instant. The crusts, already scarred by quakes, are torn apart, their millimeter ridges and fractures erased in a flood of energy. The neutron seas within, dense and defiant, surge against their own limits. For a brief heartbeat, the stars themselves blur, their identities lost in a collision that pushes matter beyond its own strength. Whether quark seas or hyperon cores lie within, they are revealed only as chaos, their structure ripped into dissolution. Radiation pours out. Magnetic fields snap and reconnect, unleashing storms of particles that stream away at near light speed. Bursts of gamma rays flash across space. The death cry of stars
them with a singularity, a point of no return. It is destruction, but also creation, the making of an object that will endure until the universe itself decays, silent and absolute. Space-time smooths again, the fabric settling after its violent ringing. The roar of gravitational waves fades as they race outward into infinity, carrying the memory of what happened here. What remains is quiet. No beams, no pulses, no signals. The system that once whispered its fate in millimeters, microseconds, and delays has spoken its last word. The double pulsar is gone. In its place, a black hole, a monument to inevitability, the final stage of matter that could not resist gravity's command. The ledger of losses has reached zero. The dance floor has vanished. The story has ended in collapse, leaving behind only silence and the faint echoes of waves rippling through the cosmos. Biased, yet the destruction does not stay hidden. Its echoes travel across the galaxy, leaving signals we cannot ignore. When the double pulsar finally merges, the event will not remain hidden. Across the Milky Way, its death cry will travel in multiple forms, each leaving a different kind of echo. Some will be seen, others measured, others inferred only by the silence they leave behind. The system may be far away, but distance cannot mute such a finale. First comes the flash. For a brief instant, the collision of two neutron stars ignites a burst of radiation that outshines entire galaxies. Gamma rays erupt as magnetic fields tear and reconnect, as matter compressed beyond endurance spews its last energy into the void. Across the sky, detectors sensitive to high-energy light would register the blaze, a sudden spike where nothing had appeared before. For astronomers, the location would become a beacon, a point etched into charts as the mark of a system's final moment. Then comes the wave. The merger rings space-time with such violence that ripples race outward at the speed of light. These gravitational waves carry the memory of the collapse, a detailed record of the star's final revolutions written into the geometry of the universe itself. When they pass, farewell. Where once there was a rhythm as steady as breath, there will be only absence. The record will break in half, the book of signals forever unfinished. Such echoes ripple beyond instruments. The merger would enrich the surrounding space with heavy elements forged in the fire of collision. Gold, platinum, uranium, the rarest substances scattered as debris. Across time, those atoms might seed new stars, new planets, even new beginnings. The destruction of two dead suns becomes the raw material for futures not yet imagined. But for us, the echoes would be reminders, a flash marking the sky, a wave rattling detectors, a silence closing the ledger of pulses. Together, they form the obituary of a system that spent millions of years tightening, losing, approaching thresholds, until finally it gave itself to gravity. Echoes in the galaxy are not merely noise, they are memory. The universe itself remembers through them, carrying forward the last signatures of stars that no longer exist. And when humanity hears them, we too will hold a fragment of that memory, a record of two clocks in one cage, ending in silence, yet leaving their trace across the cosmos. But what made this system the most destructive of all was not just its end. It was the quiet undoing that began long before. At last, the threads come together, and the name given to this pair, the most destructive system ever discovered, reveals its full weight. Destruction here is not only about the final collision, the black hole born from collapse, or the roar of gravitational waves that will ripple across the galaxy. It is about the long, patient attrition, the daily unraveling that has been underway for millions of years. The double pulsar destroys time. Every orbit stretches and compresses seconds, making clocks stumble. Pulses arrive late, dragged down by gravity's grip, and then rebound, reminding us that time is not steady but pliable. The system robs time of its uniformity, twisting it into a rhythm bent around mass and motion. For any observer nearby, seconds would flow unevenly, forever distorted by the cage of gravity. It destroys light. Beams that leave the stars do not reach us unchanged. They are stretched, reddened, thinned by the climb out of immense
its limits. Neutrons packed until they flow like liquid, electrons crushed into protons, perhaps even quarks torn loose in hidden cores. The system shows no mercy to the very substance of existence, reducing it into states found nowhere else in nature. It destroys signals. The clean ticks of pulsar beams, once flawless, become stuttered and broken as magnetospheres collide and storms erupt. Timing irregularities, glitches, eclipses, all are signs that even information cannot travel through the system unscathed. The messages we rely on to read its heart are themselves bent, stretched, and interrupted, destroyed in translation by the forces they seek to reveal. And finally, it destroys itself. Every loss of time, light, distance, matter, and signal accumulates into a destiny that cannot be evaded. The stars will collide, their cores torn apart, their beams extinguished, their identities erased in the birth of a black hole. The most destructive system does not only end in destruction, it embodies it in every moment, consuming the very measures we trust to make sense of reality. Space, time, and matter, the foundations of the universe, are undone here, not with sudden violence, but with patient inevitability. By the time the merger comes, the work of destruction will already be long complete. And yet, the origin was simple. Two massive stars, burning brightly in Puppis, reached the ends of their fuel. They ran out of ways to resist collapse. In that surrender began the chain of events that led to this. Two neutron stars circling, eroding, devouring the fabric of existence around them. The most destructive system is not a monster born of chaos, but the inevitable conclusion of stars that simply ran out of ways not to fall. The clues now align, the destruction complete. But there is still one more thought to leave behind, in the silence that remains.
When the story of the double pulsar is finished, there will be no light, no pulses, no timing strokes across the ledger of space-time. The black hole left behind will keep no rhythm, shine no beacon, and offer no hint of what came before. It will be silent, invisible except for the gravity that holds its seas, starquakes, redshifts, and precession, because of systems like PSR J0737-3039. The most destructive pair became paradoxically one of the most generous teachers. Its lesson is not only astrophysical but philosophical. Destruction is not always sudden. It can be slow, patient, hidden in millimeters lost from orbits, in seconds stretched thin, in beams dulled by gravity. The universe does not need haste to end things. It needs only time. In the end, the double pulsar will vanish into silence. But in that silence, humanity will hear its greatest truth, that the cosmos is both fragile and relentless, that even the most extraordinary systems are born of ordinary stars, and that the measures we trust, time, distance, matter, light, are themselves negotiable when gravity speaks. And so the story closes, not with a flash we will see, but with the knowledge that somewhere, far in Puppis, two ancient suns have already written their final sentence. What remains is memory, echo, and the quiet certainty that the universe is full of endings like this one, endings that are also beginnings, woven into the fabric of everything that will come after.